found experimentally that when a charged particle moves in a magnetic field, a force acts on the charged particle. The magnitude of the force is in general depend on the magnitude of the charge, it's the velocity and the intensity of the magnetic field. Furthermore, it is found that the force that acts on the body or on the charged particle is maximum when the particle moves perpendicular to the field. That is, F is a maximum for V is perpendicular to B and is a minimum is equal to 0 for B is parallel or anti-parallel to B. Connecting all these things, it can be written that the force that acts on a body on a charged particle of charge Q when subjected to a magnetic field is this. This is known as the Lorentz force. It is obviously a no work force because no F dot dr is 0. If the particle is subjected to, if the charged particle is placed simultaneously in electric and magnetic field, then the force on it will have two components. One is the electric field and another one is the magnetic field, which we call it as Lorentz force, and it is Q times E plus Q times V cross B. This is the force. We shall first try to transform this equation into the form that which will be helpful in calculating the field or the force that acts on a current carrying conductor. So our main objective is to transform this into a form which facilitates calculation for the force acting on a current carrying conductor when placed in a magnetic field. Let us first do this. Consider this is to be a conductor which carries a current I, and the cross-sectional area of the conductor is assumed to be A. A is the cross-sectional area of the conductor. So if we want to calculate I, then the I is the, if we consider a cylinder of length V, where V is the average velocity of the charges moving along the conductor, then all these charges which are within a cylinder of length V crosses a cross section in unit time. That is to say, I is equal to the number of charges within it. The number of charges within it is area A times V, the number density N times Q. So this is number density of the charge carriers, that is the number of charge carriers per unit volume, and this is A. If we want to calculate the current density, this is current density, J is current per unit area, so this is simply Q and V is the current density. Now, if we consider a conductor of small length delta L, a current element or delta R, current element delta R is considered I delta R, then the amount of charge within this volume, if we call dq is the charge, dq is equal to charge within cylinder of length delta R is equal to the charges within this is area A times dr is this is the volume times number density times the magnitude of each charge. So if this is the charge within this volume, if delta R is very small, we can assume that the same force acts on all the bodies. So the force dF on it is dq v cross b, where dq is n a q naq dr v cross b. We may assume that the velocity of the charged particle is always tangential to the where, and dr is parallel to this. So we can transfer the vector sign from v to r. In that case, we get q n a v dr cross b. Now we obtained the relation current. So this is nothing but the current. So this is I dr cross b. So if a current element I dr be placed in a magnetic field B, then the force, Lorentz force that acts on it is this. This is the Lorentz force, the form of Lorentz force which is suitable for calculating the field calculating the force which acts on a conductor. If we have a conductor in the form of a two-dimensional or three-dimensional conductor, then we can just replace this with suitable substitutes and we find the expression for the force. So the expression for force is dF is equal to I dr cross b in 1D. This is equal to Js cross b ds into d, and this is equal to jb dv and 3d. Note that we are not using primes here because the current carrying conductors are no more the source here. Rather, a field B has been created somehow and the conductor is being placed on it. So the force acts on the conductor. At present we are not considering this conductor as the source for electric field. Now we shall apply this one, this expression, that is the expression of force that acts on a current carrying conductor when placed in a magnetic field. We consider the conductor to be in the form of a wire. So that is to say we are considering this expression right now. We have a conductor, a closed conductor which carries current I, and the conductor, the loop of the conductor or the path of the conductor is called C. So the force that acts on the entire conductor is F is equal to integration over dF over the wire. So that is to say this is I dr cross b. It is over the See, the conductor may not form a closed loop, but to set a current in a conductor, the conductor must be either in the form of a closed loop or in the form of an infinite conductor. So if we have a conductor, say infinite conductor, whose one end is A, another one end is B, then this would be I dr cross B from A to B, where A and B are the endpoints of the conductor. Special case or special interest arises when the conductor is in the form of a closed loop. From our earlier discussion, we know that a closed current carrying conductor, so far an external point is concerned, behaves as a magnetic dipole whose dipole moment is given by the circulating current times area. And for small current carrying loop, we can assign a vector area to it, and which facilitates the assigning the direction to the dipole moment. So let us consider the force on a closed conductor. So force on a closed current or current loop. In that case, F will be contour integration df times if we use the Stokes theorem, an alternative form of Stokes theorem is this: dr cross B is equal to where S is the surface bounded by the contour. So if we apply this, these things becomes this will be a surface integration where S is the surface bounded by the contour C. So S is this surface area. S is this surface area. One thing is clear: if B happens to be uniform, then curl of V when nabla operating on B is 0, that is F is 0 for F is equal to 0 if B is equal to uniform field. In the case of electrostatics, we found that whenever a dipole is placed in an uniform field, no translational force acts on it. The same thing has happened here. Let me take an example to calculate the force on a closed loop. As an example, we consider a semicircular wave of radius A. So this is considered x-axis, this we consider as y-axis, this is plus A, this is minus A, and the current I is flowing through this. So along the straight part, the force along the a magnetic field B, uniform magnetic field, is applied along y direction. So B is equal to J cap B. Along this direction, the unit vector is I cap. So the current element along the diagonal. So along the diagonal, we have dr is equal to I cap dx. So df is equal to I dr cross B. So I cap dx cross j cap b. So this is the vector direction is along k cap, and this is I b dx. So the force on diagonal is obtained by integrating thus k cap I b dx from minus a to plus a. This is k cap twice a I b. This is the force on the diagonal. And similarly, if we want to calculate the force on this arc, on this path dr, along the arc dr is equal to actually a d phi prime, a phi prime d phi, sorry, not prime, d phi, that is a minus I cap d phi. So the force df on the arc is I dr cross b. This is I a minus I cap sin phi plus j cap cos phi cross j cap b d phi. So I cross j is k, so this is minus k cap I a, and then we have sin phi d phi, and j cross j is 0 and b is missing. So this is the field on an elementary arc length. So the total field on arc df on arc is equal to, we get it by integrating it from phi is equal to 0 to pi I a b So this is plus k cap I a b cos phi between the limits 0 to pi, and this is equal to, this part is minus 2, so minus k cap I 2a b. You know that these two are equal and opposite. So if we consider the total force on the closed loop, it is 0, but the force on an open loop is no more 0. This is the force on an open loop, or this is also the force on an open loop. They are not 0, but whenever a closed current carrying conductor is placed in a magnetic field, uniform magnetic field, the force becomes 0. This result could also be written in a convenient form. Let me again calculate the force that acts on a closed current loop when placed in an uniform magnetic field. For this time, we consider the conductor to be in the form of an elementary loop. Force on a small current loop. So the delta F, delta is for the small current loop. This is I dr cross B, the integration over dc, where delta C is the elementary loop. If we convert it into surface integration, this becomes I delta S ds cross B. If we assume that the surface area is small enough so that over this small surface area delta S the field does not vary appreciably, then we could write it I delta S cross nabla cross B. Sorry, there is cross B. Now we can write it as delta M, dipole moment of the current loop. This is the force on an elementary current loop when placed in a magnetic field. If V is uniform, then the force is 0. Okay. What happens if B is not equal to 0? Let me calculate this one. If we apply backup rule, then we have just used the backup rule. First, this comes out with a minus sign, and the nabla operates on B, and in second tab this will come. There is a mistake. This term should be nabla operating on this is the term. You know that the divergence B is 0, so the force on it is you consider that the when a dipole of moment P is placed in an electric field, the force that acts on it is nabla P dot E. It is the role of P is being played by delta M, magnetic dipole moment, and role of V is this. So the development of magnetic dipole moment is exactly similar, so far mathematics is concerned, to the corresponding development in the case of electrostatics or dipoles. Now we want to calculate also one thing. We may expand it into two terms and get another expression for delta F. We are not going to this, but we are going to the torque that acts on a current loop when placed in a magnetic field. So whenever we have a current loop, current element I dr prime when placed in a magnetic field, the force that acts on it is I dr cross B. So the corresponding torque that acts on it d tau is equal to R cross df. This is I R cross dr cross B. One thing we can write it I This part can be simplified as this. We have written r square is equal to r dot r, so that d of r square is equal to twice r dot dr. That is the term. The factor 2 has been adjusted. So the total torque on a current loop, total torque tau on a current loop is the closed integration of this. And we readily found that this if B happens, okay, first let me write the general expression. If B is uniform, this term goes, and we have is equal to this when B is equal to uniform. So we see that whenever a closed current loop is placed in a magnetic field, in a uniform magnetic field, no translational force acts on it, only a torque acts on it. We can change this surface this line integral into a volume integral. For this we use another form of Stokes law, which is that it is this is another alternative form of Stokes law. That we have used one form earlier. This is another form when Stokes law is applicable on a scalar point function. Earlier we applied Stokes law on a vector point function. For convenience, I am writing all the three forms of the Stokes law together. One is A dot dr over closed surface is equal to curl A dot ds, where S is the surface. If we apply the law to this, dr cross A, then the surface integration is ds cross nabla cross A, which we have used earlier, and the third form is phi dr, which we are going to use here. These are the three alternative forms of the Stokes law. Here we have used this form, and the scalar function is this. And if B happens to be uniform, then this part is readily evaluatable. This is nabla operating on xbx plus yby plus zbz. When del del x operates, it is simply B. So this part is for uniform B. This is simply B. So we come to the situation is that I ds cross B. So IDS can be considered as the dipole moment M cross B. Now if we have a small loop, elementary loop, for which it will be helpful, easier to assign vector sense. So in that case it is delta M cross B, where delta m is the vector dipole moment I times ds. Compare this with the torque that acts on an electric dipole when placed in a uniform field. It is P cross E, exactly similar expression. An application of this may be of use because many of the electrical apparatus like suspended coil galvanometer and others acts on this principle. So we consider if we consider an elementary loop, then we find in uniform magnetic field in uniform B, the delta F force acts on a closed loop is 0 and delta tau is equal to delta M cross B. We have a rectangular conductor like this. This is the z-axis. It is allowed to rotate about this z-axis, and an uniform field is placed along z direction. Along y direction, and these are the x direction. So the closed loop is ABCD. The current flows in the anti-clockwise cells. Now, these sides are parallel to the B field, so no force acts on sides AB and CD, as they are parallel, as D are parallel to B on these sides. This is first. And secondly, the force on BC, the side BC, you say that this is the field. If we assume to be uniform, then this is I cap dx, I cap dx cross j cap B integrated over B to C. This is k cap. This side is parallel, so this is k cap. I have done a mistake. This is k cap dz, so this is minus I cap I B dz integrated from A to B, B to C. If this side is of length L, then this is minus I cap I B L. So the force is along, if we consider this is y direction and this is x direction, this is y direction, then the force is on the negative x-axis. Similarly, on this side the force is along the positive x direction. So the force is again equal, the 3 F dA is equal to plus I cap IBL. So the forces are equal and opposite. So the net force that acts on the loop is 0, but the torque acts on it if the plane of the rectangular coil makes an angle theta with the direction of B, then the torque that acts on it is IBL, the magnitude of force, and if this separation is B, then B sine theta. B times A, B times L is the area. B times L is the area. If we multiply by I, then we get M. So this is M B sine theta. In vector form, this can be written as M cross B, where M is equal to LBI. And in vector sense, another thing is that we know that the torque that acts on a dipole is M cross B. If we consider the magnitude of the torque, then the magnitude of the torque is d tau for a small element, and this is delta M B sine theta, where theta is the angle between M and B. This tries to rotate the dipole. This torque, due to this torque, if we have a magnetic field in this direction and a closed current loop in this direction, then this is the direction of B, this is the direction of delta M. Then due to this torque, it will try to rotate so that the potential energy becomes zero. So it tries to align. Due to this force, this dipole will have a tendency to align itself in the direction of the magnetic field. So it leads to an potential energy del U del theta. If we integrate this, then we get U minus U0, where U0 is some reference potential, is equal to minus delta M B cos theta minus cos theta 0. In general, we set U0 to be 0 for theta 0 is equal to pi by 2. So we get U is equal to minus delta M B cos theta. This is minus delta M dot B. Note that whenever an electric dipole was placed in an electric field, the potential energy was P dot E. We can also get an expression from the force from it. So if we try to calculate force from it, we can write minus grad of U is equal to these two minus makes it plus, which is the expression of the force that we obtained in the earlier occasion. In the next class, we shall consider in this class we haven't bothered about the source of magnetic field. Here we have just assumed that the magnetic field has been produced somehow, and a current carrying conductor has been placed in the magnetic field. Special attention has been given to small current loops when placed in a magnetic field. In the next class, we shall consider that the magnetic field is produced by one conductor and other conductor is placed in the field. So as to say, the interaction between two current carrying conductors will be considered in the next class, which leads to Ampere's Force law, which is just the counterpart of Coulomb force law that we have used in electrostatics.